Right, let's start with the questions. Chemical bonding, first question. Okay, you can see here it is more to do with the statements, how the options are being given, and based on that, you need to check which of them are correct. See, first the statement goes this way. Statement one says the crystal structure of these two both show intermolecular hydrogen bonding, but are different. Okay. And second statement shows that in this they are linked together to intermolecular hydrogen bonding into an infinite chain, while in case CO3 they are connected through this dimer. Okay, this is a correct explanation. Answer is actually both are correct, and both of them are correct explanation. How is it? I'll tell you. See, C double bond O, C double bond O, O minus, O minus, sorry, O and H. Okay, O and H here, and then again it is connected to O minus, C double bond O, O and H. Again it is connected to O minus, C double bond O, O and H. So I hope you got a logic here. Now what happens? This is how, you know, the connections are being observed in the presence of, when you have NaHCO3. So in the case of NaHCO3, you would actually notice an infinite series of hydrogen bonding connections this way. So this is the structure of NaHCO3. Got it? While if it comes to KHCO3, the bonding is slightly different. You'll have this as C double bond O, O with H and O minus. And here it is bonded with O minus, which is connected with C double bond O, O and H, which is again bonded with this one. This is formed, sorry, this is formed this way because the potassium present can be at the center like this. It can be present at the center, and while it is present in the center, it can actually help in making some kind of a complex form this way. So potassium can form a better complexation with this dimer form like this. That will increase more stability. And this is what is been noticed with potassium, cesium, and rubidium as well. But wherein the sodium case, you will find the bicarbonate will be more stretchy like this. And you recall something when I told you about solubility. When I told you about solubility, I told you that usually solubility down the group should actually, you know, decrease. But we found two exceptions. One is CO3 2 minus, other one is HCO3 minus. If you remember, I told you this, right? Solubility down the group, which is expected to uh, decrease, in fact, increasing for bicarbonates and carbonates. And this is also the same explanation for it. The solubility down the group, it is increasing, clear, when it comes to, sorry, when it comes to increasing, because there is a very strong hydrogen bonding lying in NaCO3 here. So that will be very stretchy like this. Got it? Because of which it becomes difficult for it to make easily soluble in the water. Clear, everybody? So the statement, both of them are correct, and that is a correct explanation as well. The second one. SnCl2.2H2O readily loses one molecule of water at 800 degrees Celsius because one because what are the options here? You can see A, B, C, D are given here. One water molecule is coordinated to SnCl2 and the other is hydrogen bonded to coordinated water molecule. Okay, right. Now again, this is a very factual thing, but it has been asked in JEE before, so please learn this. That SnCl2, if you notice by structure, how is it? Basically, it will have one lone pair here, chlorine here, chlorine here, and one water molecule here. This is how it is making an sp3 hybridized pyramidal structure. Pyramidal structure. And Out of this structure, the oxygen present here will make a hydrogen bonding with the other water molecule this way. Okay. Of course, here also there is a bonding, but like I said, in inorganic, we do not call it as a hydrogen bonding here. So how many hydrogen bondings? We have one hydrogen bonding, which you have it here with this oxygen. Clear, everybody? So that's how this can be isolated. This molecule, when you crystallize, can be isolated. So it appears as if you have SnCl2 dot 2H2O. But in fact, if you see the structure, this is how it appears to. Yeah. So which one is more appropriate here? So I think the first one. Done. Clear, beta? Next. Identify three-centered two electron bonds in this case. Okay. Now that means you have to notice a bridged bonds. We have to notice a bridged bonds, which is three-centered two electron bond. Now obviously we can figure out that beryllium with these two hydrogens. Sorry, this is bridged bond, correct? And here, sorry, here there is only single electron being shared like this. So you can notice that here there is three center two electron bond, here there is three center two electron bond. But the minute you get chlorine, fluorine, what will they do? Of course, this is not even showing any bond because it already has a back bonding that is helping it. Okay. So while in the case of AlCl3, it will get dimerized, but this time it will be three-centered four electron bond. Now notice another example. I'll add it up here. Is one example is BH sorry B2H6, which we learned it. The other example is Al2 CH3 six times. So just like this one, we have methyl groups, two methyl here, two methyl here, and there is one methyl here like this. There is one methyl here. Methyls are also like hydrogens only because carbon is not carrying any lone pair. So here you will see one electron and one electron here and one electron. So what kind of a bonds it is making? Three center two electron bond. So remember, by chance instead of halogens, methyl is given anywhere, which means it is carrying three center two electron bond. Everybody, examples are clear? So make any doubt in this? Right. Next. Nodal planes of pi bonds in this four carbon allene are located in which particular position? Four carbon allene, where are they located? Okay. Nodal planes are those planes where you do not find any electron at all, isn't it? So if you notice, when it comes to four carbon allene, let me put it like a plane here first because all of them will be planar only, like this. So notice this one, we have carbon here with two hydrogens on this plane. Then we have another carbon here, another carbon here, another carbon here with two hydrogens on the same plane, correct? So all the atoms are on the same plane because it is an even carbon allene, which means where is a pi bond exactly? One pi bond will be above here, correct? Like this. Let me show you with the glass here, like this. Between these two, there is one pi bond which is above and below the plane, and there is one pi bond here which is on the plane, and there is one pi bond here which is again above and below the plane, like this. This is how the pi bonds are, everybody. Okay. Now go to the options and check what is the question asked. Here. Now, what is it said? Nodal planes of pi bonds in this are located in where? See, for this pi bond, what is the nodal plane? This itself is a nodal plane, correct? For this pi bond, what is a nodal plane? This one, the perpendicular form will be the nodal plane here. Let me write that also. Okay. So this is another perpendicular plane which I'm talking about. Like this. This is the perpendicular plane. So that perpendicular plane will be nodal plane for this pi bond, isn't it? And again for this pi bond, this is the same nodal plane. So how many nodal planes we found? One nodal plane is actually the same for this pi bond and this pi bond, correct? So only one nodal plane for both the pi bonds. And this is one nodal plane for this pi bond. Did you agree with that, everybody? So how many nodal planes, everyone? Maximum you can get only two nodal planes for the pi bonds. So one is perpendicular to the other. Now go with the options. All are in molecular plane? No. Two are in molecular plane and one is perpendicular to the molecular plane. That is correct. Make sense? Everybody? Right. Let's go ahead. The correct increasing order of the extent of hydrolysis is, okay. If you want to check out the extent of hydrolysis is, you know, extent of hydrolysis means what? That means when you add it to water, it should start absorbing more number of water molecules. Correct. Clear? Now notice what is the kind of bonding that it makes. See, first check out the oxidation state. Oxidation state, I told you, oxidation state is a temporary charge or the hypothetical charge which we assign to say what is its polarity. So phosphorus is losing kind of 5 electrons to 5 chlorines. We can say approximately it has around +5 oxidation state. This has +4, this has +3, this has +2, this has +4. Okay, this is the state which it has. Clear? Now notice what is happening here. So in the case of, see, if water molecules have to, lot of water molecules have to accumulate, correct? Then you can definitely remove all these chlorines and then make the water to accommodate onto this one. Okay. So I can remove all the 5 chlorines here and I can accommodate with 5 water molecules in this case. And that will eventually convert into H3PO4. I can do the same thing with silicon. Also, all 4 chlorines can be removed and 4 water molecules can be accommodated. I can do the same thing with aluminum also because, see, why we can do it? It has an empty d orbital. This has an empty d orbital. This has an empty p orbital. Okay, there is an empty p orbital in aluminum. This also has an empty p orbital. Correct. So water will be initiated to make a bonding or extent will be increased only when there is an empty orbital there. So this has empty, this has empty, this has empty, and this has empty. But the only problem with CCl4 is it does not have any empty orbital. So that is why CCl4, if you add it to water, nothing will happen. It is insoluble. Correct? But rest all of them are soluble in water and they will start extending, bonding with water molecules, slowly losing out all the chlorines. Got it? Right. Now, this we will study as a separate chapter in term called GIC. Before I start with S block and P block elements, I will teach you GIC, wherein I'll teach you how to do the hydrolysis. Okay, hydrolysis is a separate topic, but I'm sure you got a basic essence of it. That as you have more number of, sorry, if you have an empty orbital and higher oxidation state, definitely you will have more extent of hydrolysis. Okay, right. See the next question. Oh, so what is the best option? A. Okay, next. In which of the following species d orbital have xz and yz two nodal planes are involved in hybridization of central atom? Xz and yz two nodal planes are involved in hybridization of central atom. Okay. Okay. First, let us figure out what is the steric number in all the cases, everybody. Such cases, you always try to figure out what is the steric number. Steric number is half into, this is 7 plus 2 plus 1. So how much it is? 5, which means it is sp3d. Now, have you noticed there are 4 atoms, 5 connections, which means one should be lone pair, correct? And what kind of a d must be involved here? This is usually dz square. So are we involving any xz and yz orbital here? No, we are not using these orbitals, correct? Second case, here steric number is half into 7 plus 4 plus 1, right? So 12, so 6, so this is sp3d2. So what type of d are involved in this case? dz square and d x square minus y square. So we are not using that either here. Here, next is IF7. In the case of IF7, what are we using here? H is equal to half of, right? Um, what is that we are using? So 7 plus 7, which makes it total 14 by 2, 7. So it is sp3d3. Okay, this is sp3d3. Clear? Right. Now notice xz and yz has to be the nodal planes. What does that mean? Which orbital will have xz and yz as a nodal plane? Let me remind you something which we learned from structure of atom. Suppose if you have d orbitals, if the d orbital is like this with x and y here, correct? Then z axis is coming out of the plane. Barabar? What is this orbital? This is xy, dxy orbital. So what will be its z-axis here? Z-axis will be like this, right? It is coming out of the plane this way. This is the z-axis here also. This is the z-axis like this, isn't it? Now, what are this one? This is xz plane and this is yz plane, correct? This is xz and yz plane, isn't it? And have you noticed there is no electron present on xz and yz plane? So which means what are those two? Nodes. These two are nodal planes. Which means for which orbital xz and yz are nodal planes? These are nodal planes for dxy. So isn't that what the question is being asked? Now let's get back to this. What is the d orbitals which we are using for hybridization in this case? We are using dz square for sure. Then we are using dx square minus y square. And then we are using this as, you know, dxy. So when you use these 3 orbitals, that's when you will have the hybridization as sp3d3. Everybody clear on this question? Samyak, any doubt? Sure. Utsa, keep responding. Utsa, are you following? Anna,
Yes, sir. No doubt, sir.
Ishman,
No doubt, sir.
Shauri, Shaur, could you please respond? Utsa, what happened? Beta, your connection, you're getting lost with your connection. Are you okay? Are you able to connect back? Utsa, right. See, next. The longest CC bond is present in which of the following compound? Okay, this is a very good question, everybody. Got it? This is one of the applications of Bend's rule. There are a lot of questions like this in VK Jaiswal. If you understand one of them and the trick is clear, then you'll be able to answer all of them very easily. Now tell me about it. Suppose, first we'll start with a basic example. Let's say if you have hydrogen, 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 correct? Since carbon is sp3 hybridized, what is the percentage s character in this orbital? It will be 25% only. In this orbital, 25% only. Because it is uniform, it will be 25%. Here also it will be 25%, correct? Everybody, it will be 25% in all the cases, correct? Now, let's see the trick. Suppose if you have three hydrogens, but then I replace one with chlorine. Replace one with chlorine. Okay. Now what happens? This will supposed to be 25%. It is supposed to be 25%. Now it will be greater than 25%. Here also it will be greater than 25%. And here also it will be greater than 25%. But only in this bond it will be lesser than 25%. That means even though orbital is the same, it is sp3 hybridized only. Now what happens? Earlier in the case, the shape of the orbital and the size, the length of the orbital is same in all four of them. But now what happens? Here, the shape will be like this, but here it will be slightly elongated. This fourth orbital, which is connected with chlorine, right? अब ये थोड़ा सा बढ़ जाएगा. Why is that orbital elongated? See, problem what is happening is chlorine is more electronegative than carbon. So its natural tendency is to pull the bonded electrons towards itself. But carbon cannot lose the claim on those electrons, right? So carbon cannot say these electrons, they're gone. I can't, I mean, it's not for me anymore. To make sure those electrons are still making a better, I mean, those electron cloud is making a better overlapping or better sharing with chlorine, what will carbon do? It will try to keep this orbital more stretched. So when your central atom or a hybridized orbital is being connected with a more electronegative element, naturally that particular side of the orbital will start stretching more. Acha, if you want to stretch an orbital, which character will be more helpful, S character or P character? P character, because P are more directional, right? So that's why the percentage P character will start increasing in this orbital and percentage P character will be decreasing because overall percentage P character is same. So it will borrow some P character from other three orbitals and try to push that P character into that fourth lobe. This way, what happens to the other three or lobes? These three lobes will start gaining more S character and less P character. So, since all of them were supposed to be 25%, now the percentage S character will be more in it, and this orbital will have lesser percentage S character and more P character. Is this making sense, everybody? Now, guys, tell me, if the S character increases, what happens to the bond length? Decreases. If the P character increases, what happens to the bond length? Increases. Correct? Is that clear, everyone? Now, let us apply this into the questions. Check out. The longest C and H bond is. See, here between carbon and carbon, there is one sp3 character here, right? This is sp3 and another sp3 coming from this end. Here, another sp3 coming from this end. So, this sp3 carbon is this one. The other one is sp3 carbon from here. Now tell me, since there are three fluorines, it must have drained all the P character into it, correct? So the only lobe which is present on this side, does it have more P character or more S character? Now here, for this orbital, high S character is present, isn't it? Everybody? It has very high S character, right? So you know how the lobes would be? The lobes would be something like this. ये ऐसे रहेगा. Other three lobes are like this, correct? while when it comes to this CF3 ये ऐसा रहेगा lobe. This is how the lobe will. Everyone got an idea? सबका दिमाग चल रहा है ना? ये बहुत इंपॉर्टेंट एरिया है. Okay,
Sir,
right. Yes beta.
sir, could you repeat it again?
Yeah, no problem. Listen, what I said, between this carbon and CF3 beta, it is this carbon is also sp3. Agree with me? That is also sp3 hybridized. 4 single bonds are there.
Yes.
इसका मतलब वो it is sp3. So 3 fluorines are strongly withdrawing because of their electronegativity. What would they demand the carbon it is connected with? It will demand boss पूरा p character मेरी तरफ भेज दो. So this carbon, you know, is bound to push lot of p character into the orbitals where it is bonded with fluorine. This said there is fluorine bonded like this. Okay. So where fluorine is bonded, it has to push all the p character. If the p character is pushed, the only other lobe which is present in this one, वो क्या हो जाएगा बेटा? वो shrink होने लगेगा. Because उसमें s character develop हो जाएगा and p character will diminish. And like I said, if the s character increases, length decreases. P character increases, length increases. Clear beta? Is
Okay,
this clear
sir.
now?
Yes, sir. Thank you,
Right,
sir.
Sweta. Right. Because of which here this much will be the length. Okay. Now have you noticed something? Here there is one fluorine, here there is one fluorine. तो यहाँ पे दोनों तरफ से खींच रहा है. तो what happens to the orbital length now? It will be like this. Correct? One p will be like this, other will be like this. Here two will be like this, the other will be like this. Correct? Sorry, put it more decent. Like this. Got it? And what about the C1? If you have two fluorines here, और भी ज्यादा stretch हो जाएगा outward, and between the carbons the length will further keeps decreasing. Now tell me which one has the smallest bond length out of these four? The D part, isn't it? Because can you notice अभी कैसे होगा orbital? This is how the orbital will be. This is CF3, this is CF3 here, and this is CF3 here. So this will be the shortest carbon-carbon bond length, single bond length, single bond length. Correct? So from the given data, from the given examples, which one do you think will be more correct? Which of the following will have more? Now notice this one. Here the drag is too much. Correct? All three fluorines are coming. So ये बहुत छोटा हो जाएगा. Here at least one fluorine is here, one fluorine is here. इसकी वजह से drag is not that high. So which one will be the longest one here? This one. Got it? So everybody, what is the correct order? You know, it is B greater than C greater than A greater than D. This will be the bond order, longest carbon-carbon bond length data. Everyone clear on that? Next, see the eighth one. Incorrect statement of N2F4 and N2H4. In N2F4, the d orbitals are contracted by electronegative fluorine atoms. Okay, d orbitals d orbitals are contracted by electronegativity of fluorine atoms, but the d orbital contraction is not possible by hydrogen in N2H4. Okay, next, the Nn bond energy in N2H4 is more than Nn bond energy in N2H4. Next, this one. Again, we just have to apply the Benz rule here, nothing else. Okay, now tell me, in N2F4, the d orbitals are contracted by electronegative atoms. Where are the d orbitals present in this? but the d orbital contraction is not possible by H atoms in N2H4. Please tell me, do we have any d orbitals present in it? Everybody? No. So is this statement actually valid? No, right? Neither the d electrons are in present, d orbital electrons are present in nitrogen or fluorine. So this one is definitely wrong. See the second statement. The N bond energy of this one is more than N here. Now again, N2F4 is like this, everybody. Okay, N2F4 would be like this. N with a bond here like this, and other fluorines will be bigger like this. While here, on the other hand, will be two hydrogens which is of the same kind like this. This is N2, sorry, this will be N2F4 like this. So the bond length is smaller here, but if it comes to N2H4 like this, here they will be smaller this way, isn't it? Now tell me, where is the bond length longer? Bond length is longer in N2H4. So if the bond length is longer, energy required is less. So it is easy to break N2H4 as compared to that of N2F4. So that means this statement is correct. Next one. Nn bond length in N2F4 is more than that of, this is incorrect again. Just now we discussed that it is shorter. Nn bond length in N2F4 is, this is correct. So which of these two are incorrect here? 1 and 3. Clear, everybody? Which of the following species absorb maximum energy in HOMO-LUMO electronic transition? The other day I told you, whether you are removing the electron, whether you are adding the electron, that becomes more significant here. Okay. Now, if the energy difference gap, sorry, I mean the energy gap or the energy difference between the two orbitals, that is from HOMO towards LUMO, if the energy difference is more, then the energy absorbed will be more, and the wavelength absorption wavelength will be less. Okay, so sometimes the question might be asked in terms of maximum energy or minimum wavelength. Now let's see where exactly the electrons are present. Okay, the HOMO orbital of O2 is what? Pi star 2px1, pi star 2py1, and sigma star 2pz. These are the orbitals. Next, N2 minus. N2 minus is what? N2 minus, we have sigma 2pz2 and pi star 2px1 and pi star 2py0, and then we have sigma star 2pz0, right? This is the configuration of N2. C2 is um, C2 we have, yeah, sigma 2pz2, and then we have pi star 2px and pi star 2py0. N2 is N2 will be, sorry, here I made a mistake. This one is pi 2px. Now pi is what we need to have now. Pi 2px2 and pi 2py2. Yeah, this is where 12 electrons gets completed, and then we'll have 2pz0. Then we have here uh, sigma 2pz2, and then we have pi star 2px and pi star 2py0 and 0. So if you could just recall the last set of energy difference, you can see this is what it is. Usually the energy difference will always be maximum between a bonding kind and an anti-bonding kind. That's a general trend. Now notice if an electron is present here and from here to here it is going from antibonding to antibonding only. So the energy required will be less. Here also it is going from antibonding to antibonding. Energy required will be less. Okay. Here it is going from bonding to bonding. Again, energy difference will be less. Here it is going from bonding to antibonding. So here energy required will be more. Clear everybody? So which homo-LUMO difference will be more here? D. Clear? These kind of questions you always try to figure out where is that extra difference which you are getting. Any doubt? The next one. If CdI2 is pink in color, can you think of it? What color it could be? Now, problem here is, see, this is a very controversial question, I would say. See, zinc, cadmium, and mercury, all of them have a configuration of Ns2 N minus D 10. This kind of a configuration is called as pseudo inert gas configuration. Pseudo inert gas configuration. If you have pseudo inert gas configuration, there is no excitation of electrons here because electrons are very stable in their states. So you will hardly find any electron to take energy and go into the higher orbit. Got it? So that is not how the electron transition will happen. Okay. So since electron transition is not happening this way, we cannot predict the color. But then you say, sir, what if there is a transition? Then how will we predict the color? Okay, let me tell you that. You always go with something called a color wheel. This is a color wheel. Okay. So as per color wheel, notice this 6 colors here, which are broad colors. These are called broad colors. V, B, G, Y, O, R. Okay, correct. And in fact, the pink shade would eventually come somewhere here. The pink shade will be at the end here. Correct. Rest all will be this red color. The pink, it will start becoming at the end. And thereafter, it will start giving you that purple color. So here that will be purple, and that purple slowly will start, I mean violet, it will start converting into violet, and from there to indigo to blue. This is how the conversion starts. Okay. Now notice it. If you compare the wheel, this is the direction in which the lambda absorption is increasing. That means if electrons absorb energy, correct, the amount of energy absorbed, if you compare its respective lambda, that will be increasing in this direction. What I meant to say, imagine if I say a compound is absorbing violet color and I say a compound is absorbing green color. So who is absorbing more energy or a higher energy? I would say violet color. Understood? That means the compound which is absorbing violet color light is absorbing more energy because its wavelength is less. Is this part clear, everyone? Now, if I see something as a pink color, correct? If something as a pink color, then its complementary color will be somewhere here, which is light green. The complementary color will always be on the opposite side. complex is absorbing yellow color, then what is the color what you will see? You will see it as violet. Okay, everybody. Here, if you see, this is a light yellow color. The t-shirt which I'm wearing is light yellow color, correct? Which means what is the t-shirt? The t-shirt's surface atoms which are present on this t-shirt. What it might be absorbing, everybody? It might be absorbing indigo. Indigo is somewhere here. That indigo will make it a light yellowish color here. So because you are watching in light yellow, that means it is absorbing indigo color. Everyone clear on that? Suppose if you see this one is a blue color stick. It's a blue color. So if this is a blue color stick, right? Then what might be absorbing? Definitely that surface is absorbing orange color. That's why we are able to see it as blue color. These are called complementary colors, everybody. Now tell me, if it comes to CdCl2, suppose compared to that of uh, CdI2, CdI2 and CdCl2, I'm comparing these two. Which one do you think will absorb, okay, more amount of energy to go to the higher orbit? Obviously, chlorine will absorb more because the energy difference for chlorine would be more compared to that of iodine, isn't it? Energy difference for the orbitals because iodine is much stretched orbital, so the energy difference will be less. So that's why chlorine would be absorbing more energy. Okay. So now if CdCl2 is appear to be pink, that means what is it absorbing? It is absorbing somewhere color here, isn't it? That means CdI2 is absorbing somewhere light green. Got it? It is absorbing somewhere light green. Now tell me what could be CdCl2 absorbing in that case? CdCl2 has to absorb somewhere blue or violet because you know the energy absorbed should be more because CdCl2 energy difference of the orbitals will be higher energy orbitals difference will be more. So what kind of a colors it should give? It should give probably yellow or orange or maybe some part of green, red. Okay, clear everybody? So one thing is for sure it cannot give blue. So it could have been either red or yellow. But since this is a pseudo inert gas configuration and since electron may not be excited, so we cannot predict the exact color. So here the answer is D. But in other cases, if you know electron is excited, then I hope you know now you understood how to judge everybody. This concept doesn't end here. We have a separate chapter for it. Don't worry. Okay. So again, we'll be inorganic. We'll be keep on coming across these colored questions multiple number of times in P block, in coordination compounds, in D block. You'll keep on getting this. Every time that comes, I'll keep on making you more comfortable with color wheels. Okay. Right. Next, check out this one. Which order are correct? Thermal stability, basic nature, solubility in water, and melting point. First, thermal stability. What was the first thing I told you? Easy way to predict thermal stability, guys. I categorize them into two kinds, right? One is single anionic species. The other one is multi-anionic species. What is this one? This is multi-anionic, right? Sulfate is a multi-anionic. So if it is multi-anionic, what happens to the stability down the group? Increases. For single anion, what happens to the stability? Decreases. Please try to recall it, everyone. Single atomic anions, down the group stability decreases. Multi-atomic anions, down the group stability increases. Okay, so thermal stability, is this correct or no? Yes, it is correct. Everyone clear? See the next one, basic character. Basic character, right? Left to right, actually it should decrease. So most basic should be calcium oxide, then magnesium oxide, then beryllium oxide, and last comes zinc oxide. So this is exactly given ulta. Remember, for oxides, left to right, basic character decreases. Down the group, it increases. Solubility in water, hydroxide. Hydroxide is a when it comes to ionic solubility. What was the two categories I told you? One is small size anion, the other one is large size anion. If it is small size anion, down the group solubility increases. If it is large size anion like sulfate, nitrate, bromate, sorry, iodate, or chromate, dichromate, manganate, oxalate, right? Carbonate. Carbonate are two exceptions, only for group 1. Hmm? But otherwise, all the compounds which are bigger in size, down the group solubility decreases. If it is smaller size atom, oxide, fluoride, chloride, hydroxide, cyanide, nitride, for all of this, what happens down the group? Solubility increases. So that means this is given correct. Okay, sorry, this is given wrong. Hmm. Down the group, he said it is decreasing, right? In fact, it should increase. Last one, melting point will be in this order. This I told you have to mug up. Okay. In this case, NaCl will be higher and LiCl will be the last. Done. So which are correct here, beta? 1 and 4. Clear? Now see this question. The correct order of solubility. Okay. You should be able to tell me now. This is an exception for group 1, but not an exception for group 2. So what should happen down the group? Down the group, solubility should increase in general. Sorry, decrease in general. But for group 1, it will increase. Hmm? Correct? Everybody. Down the group, in general, solubility should decrease. But for group 1, it increases. Right? So based on that, what we can say? Is first one correct? Solubility, which is correct, isn't it? Is second one correct? Down the group, it is increasing, correct. Is third one correct? Correct. Is fourth one correct? Wrong. Any doubt? Right. Check out the 13th one now. Which of the following has non-zero dipole moment? Okay. See, like I said, first thing what you will check out is the hybridization. Based on hybridization, you will try to predict the shape. And once you predict the shape, you will try to figure out how the vector sum is. Is the vectors getting cancelled or is there anything else remaining? So first thing I will do is figure out H, which is half into chlorine is 7 plus 3, which makes it sp3d. Second one, H is also equal to half into 5 plus 5. So which is again 5, which is sp3d. Because all of these are monovalent. CCl3, CH3 are monovalent. Xenon half into 8 plus 2, which is 5. So sp3d. Here, this is a special case I told you in back bonding, tricylyl amine. So it was supposed to be sp3, but because of its back bonding, it will be sp2. Correct. Now in the first case, chlorine, which is more electronegative, everybody? Fluorine or oxygen? Fluorine, right? So as per Bend's rule, we are supposed to place fluorine axially first. And then one fluorine will be here, other two oxygens will make double bond this way. This is the structure. Second one in Xc is Xc, fluorine and fluorine, double bond O, double bond O, double bond O. Next, third case, fluorine, CCl3 is more electronegative, which will go like this, but CH3, CH3 and CH3 will be like this. Last one. Nitrogen, it is triangular planar. It will be like this. SiH3, SiH3. Now you guys can easily predict now. So mu here is non-zero, mu here is 0, mu here is 0, mu here is 0. So tell me which one has the dipole moment? First one. Very, very important question. Asked so many times. Same logic, same type of questions in advance, asked multiple number of times. Correct? With different compounds, but the logic is the same. This is what you need to do. Specifically, questions are aligned for sp3d more. Correct? Very good, Utsa. Everyone, is this clear? Right. Okay. So I suggest now rest of the questions you will try them first. Correct? So next class, the first thing I'll do is I'll discuss all the questions. Correct? The first thing I'll discuss all the questions and I'll upload this particular file right now so that you are at least you can go through the questions whatever we discussed. Rest of them you finish them, and after that I have given you the assignments. You can attempt those questions. Clear? Everyone clear on that? Okay. uh Again, I'm giving you an option. Whoever is comfortable doing vkj as well, you can please go ahead with it, complete it. But if you feel there are too many questions, you don't know us, there is a juggling around topics, I have assigned you assignments completely uh, subtopic wise. Okay. So if you are uncomfortable in particular topic first, you can go through the subtopic wise, complete those questions, and then go to VKG as well. Correct? But primarily finish this assignment first and then do the rest. Okay? Right. Any other doubts?
So after this chapter, we'll do thermo now.
Yes, beta, thermo. We'll start with thermo. Is there
ठीक है ठीक
anything
है।
you have in mind? Let me know.
नहीं नहीं सर, थर्मो ही ठीक है, हमारा भी वही करेगा उसके बाद।
Perfect. बाकी